In this video, we're going to talk about applying multiple transformations to a function. And our goal in doing this is to think about applying transformations graphically, symbolically, and also examining when the order of transformations does and doesn't matter. So let's start with a function. So here is a function I'm going to start with. We can call this f of x, and we're going to think about composing these transformations both graphically and symbolically. So I want to start with graphically, and here are the two transformations that I want to do to the function. So the first thing I want to do is reflect over the x-axis. And the second transformation that I want to do is I want to shift up by 1. So let's carry these out graphically first. So if I reflect over the x-axis, I'm going to take each of my outputs and take their opposite or their negative. And so the result of doing that is going to look like this pink function here. Okay, now I want to shift that result, that pink graph, up by 1. So I'm going to take each of those outputs. 0 is going to go to 1, -1 is going to go to 0, and 0 is going to go to 1. And so my final graph, after first reflecting over the x-axis and then shifting up by 1, is going to look like this orange graph. Let's see what that looks like symbolically. So if my original function is f of x, when I reflect over the x-axis, I'm taking the opposite of all of those outputs, and so my resulting function will be negative f of x. And now what I'm going to do is I'm going to take those outputs, negative f of x, and to all of those outputs, I am going to add 1. Okay, so the final result of doing both transformations is going to be a new function, which I can call h of x. And h of x is defined to be negative f of x plus 1. Let's use a point to check and see if this final formula is correct. So I know that a point on my graphically doing these transformations, I know that a point on h of x should be the point 2, 1. So what that means is when I plug 2 into h of x, the output should be 1. So let's check and make sure that's the case. So I'm going to check by plugging in h of 2. Now h of 2 is defined to be negative f of 2 plus 1. Let's see, what is f of 2? F of 2 was our original violet graph here, and f of 2 was 0. So I have negative 0 plus 1. So this whole thing is equal to 1. So when I take my new function h and I plug in a 2, my output is 1, which is exactly what I saw should happen graphically. So here, I did the transformation graphically, and I used this point to check that this symbolic work I did was correct. Okay, next we're going to see what happens if I do these same transformations in the other order. Will the order matter or not? And what is it going to look like? So I'm going to step over here and do the same thing and do these in the other order. So let me redraw my graph here. So here is my graph again of f of x. Let me add a couple more points here. Okay, so again, this is my original graph f of x, and now I want to do these transformations in the other order. So first, I want to shift up by 1, and then I want to reflect over the x-axis. Okay, so before I draw that, take a moment to try to imagine this in your head or to sketch this out in front of you. What will this graph look like if I shift up by 1 and then reflect over the x-axis? You can push pause if you want to do that. I'm going to start drawing it. So I'm going to use some new colors here so we don't get too confused. So shifting up by 1, all of my outputs are going to shift up 1. So 0 will become 1, 1 will become 2, and 0 will become 1. So this is the result graphically of shifting up by 1. Now, what's going to happen when I reflect over the x-axis? This is where things start to get interesting. This output of 1, when I reflect over the x-axis, is going to go to -1. This output of 2 is going to go to -2. And this output of 1 is going to go to -1. I'm going to use double lines here so you can see the difference between this and the original graph f of x. Okay, so again, we shifted up 1 and reflected. And what we should notice right away is that my final graph here is different than my final graph over here in orange. Okay, so graphically, it definitely seems like the order matters. Reflecting then shifting gave me a different final function than shifting then reflecting. So let's see what's happening symbolically here. So when I shift up by 1, I'm taking my outputs from f of x and adding 1 to them. So this is the shifted function. It's all my outputs from f and adding 1 to those. Now, when I reflect over the x-axis, what's a little bit different here than before is I'm taking all of those outputs and I'm taking the opposite of the whole output. Okay, so I need some parentheses here. And my new function is the negative of f of x plus 1. And that's different than negative f of x plus 1. So let's give this new function a name and check that what we concluded here matches what we concluded graphically. So I'm going to do the same thing. I'm going to highlight a point that's on our final graph. Let's take the point 2, -1. And what 2, -1, the fact that that's on our graph means that when I plug 2 into this expression, I should get out -1. So let's see if that's right. G of 2 is equal to negative. Plugging 2 into G means plugging 2 in everywhere I see x, plus 1. So that's negative. F of 2 is still 0. This is my original f of x. And so this is equal to -1. So what this did for me is this was a check that my symbolic conclusion that g of x was negative of the quantity f of x plus 1 matched what I concluded graphically. So I plugged in the input 2 and I checked that I got the output I expected, which was -1. So this is a helpful way to check that my symbolic conclusions are correct. Okay, so we're seeing that our formulas are different, our graphs are different. One last thing I want to point out here is that if I distribute this negative sign, there was more than one way to think about how to get from this original function f down here. We thought of it as shifting up 1 and reflecting. We also could have thought of it as reflecting and then shifting down 1. And interestingly, we can see that here when we distribute the negative sign. We see what this is this is a reflection first, followed by a shift down. And so what we're seeing, let me just dot that in here, is we could have shifted up 1, then reflected. To get to the same place, we also could have reflected first and then shift down 1, and that's exactly what we see symbolically when we distribute that negative sign. What we're going to do next is we're going to look at if the order always matters. So in this case, we've seen, yes, sometimes the order definitely matters. And so coming up next, we are going to look at a different case where it's going to work a little bit differently. Okay, so now what we're going to do is we're going to look at another pair of transformations. So let me start again by drawing our function. So I'm going to have a new function f of x. Let's see. Just for the sake of interest, we'll make a new function. So this is our new function f of x. And I'm going to choose two new transformations, and we're going to apply them like we did before and see if the order matters. We're going to do this graphically and symbolically, and we're going to use points to check our work. Okay, so this time the two transformations I'm going to apply. The first transformation is I'm going to do a horizontal stretch by a factor of 2. And then I am going to shift down by 1. So let's do these two transformations graphically first, and then symbolically, and then we're going to try them in the other order. Okay, so a horizontal stretch by a factor of 2. I need a couple more marks on my axes here to do this. This means from the y-axis, everything is going to be stretched by a factor of 2. So where I used to have an input of 1, I now have an input of 2. Where I used to have an input of 2, I now have an input of 4. So my whole graph has been stretched horizontally by a factor of 2. Now I want to shift it down by 1, so all of my outputs are shifting down 1. So I'm going to take my pink graph and shift all of my outputs down 1. Okay, and that is the result of first stretching horizontally by a factor of 2 and then shifting down by 1. So let's look at what happened symbolically. So if my original function here, we'll use the same name as before. We'll call this f of x. If my original function is f of x, one thing we can remember is to stretch the graph horizontally by a factor of 2, you might recall that we actually need a factor of 1/2 here, not a factor of 2. We can kind of check quickly why that is. So if this is my pink function, you'll remember from some of the other videos, if I plug in a 4, right, I want the point 4, 1 on my graph. If I plug in a 4 as my input, it first gets scaled down to 2, then gets plugged into f and gives me my output of 1. Okay, so the reason this is kind of acting opposite is it's acting on my new inputs and kind of squishing them back to my old ones. So if I want my new inputs to be stretched out, I actually need the factor of 1/2 here. Okay, so this is my function that's going to give me this pink graph. Now, to shift down by 1, I'm going to take that function and subtract 1 off of all those outputs. Okay, and I can do the same thing to check a point here. So let's take the point. This is a point on my orange graph, 2, -1, and we can give this function a name and check that when I plug in 2, I get the output of -1. So let's do that. H of 2 equals, what it means to plug 2 into H is to plug 2 in for X everywhere I see it here. So f of 1/2 times 2, that's the same as f of 1. If I go back to my original function, f of 1 is 0. And I ultimately get -1. And that's exactly what I wanted to get. The point 2, -1 was supposed to be on my final graph. And what I saw is when I plugged in a 2, I got out a -1, which is a very good clue that my formula here is correct. Okay, now let's do this in the other order and see what happens. So remember in our previous set of transformations, the order mattered. We got 2 different things. So let's see what happens this time. So I'm going to do these in the other order. So that means first, I am going to shift down by 1, and then I am going to do a horizontal stretch by a factor of 2. And before I start to sketch this, pause the video, sketch it for yourself, or try to imagine in your head, what does this look like? Okay, so shifting, starting with the violet graph, what does it look like to shift down 1 and then horizontally stretch by 2? Okay, hopefully you've drawn that for yourself or imagined it. I'm going to sketch it now. So I'm going to start with my violet graph again. I'm going to shift down by 1. So this is -1 here. And then I'm going to stretch horizontally from the y-axis. All of the inputs are going to be scaled by 2. But that means this point, 1, -1, when I scale my inputs and stretch them, it's going to go to the point 2, -1. When I stretch this point here, 2, 0, and stretch the inputs by a factor of 2, it's going to go to 4, 0. So the result of stretching this neon green graph is actually the orange graph. So let's take a step back. What we've just seen is that in this case, the order didn't matter. We could stretch it first and then shift down, or we could shift down and then stretch it. So how is this case different than our last one? Why didn't the order matter? So the big moral that I want to share here is that if we apply 2 transformations, one of which acts on outputs, or another way to say that is it acts vertically, and the other of which acts on inputs, or another way to say that is horizontally, then the order doesn't matter. Okay, so in our first case, our reflection was acting on outputs, and so was our shift. And then the order mattered. In this case, one transformation is acting horizontally, and the other is acting vertically or on the outputs, and in this case, the order doesn't matter.